When astronauts look back at our planet, they experience what's known as the overview effect. From the vacuum of space, this blue marble looks completely serene, a quiet, static object hanging in the dark. That peaceful image hides a much harsher reality. The rest of our solar system is a graveyard of irradiated rocks, of frozen moons, and planets blanketed in toxic gas. We often attribute our existence to Earth's lucky position, setting at exactly the right distance from the sun. But a good parking spot doesn't automatically create a biosphere. Earth's habitability is an extreme anomaly that requires constant, active generation. The planet operates as an interlocking mechanical engine. Every physical layer we see, from the clouds down to the soil, depends entirely on the active functions of the layer immediately below it. Understanding our survival requires descending into the mechanics of this planetary machine to see what happens when a single gear stops turning. This descent begins 6,000 kilometers underground. Down here, the core reaches temperatures of up to 6,000 degrees Celsius, driven by primordial thermal energy and the continuous decay of radioactive isotopes. This intense heat causes the liquid iron and nickel in the outer core to boil and churn. This continuous convection of liquid metal acts as a massive electrical generator, creating a geodynamo. This geodynamo generates the magnetosphere. As shown in this diagram, these invisible magnetic field lines project into space to deflect a continuous barrage of charged particles from the solar wind. Without this shield, supersonic winds would strip our atmosphere into space. That internal heat must constantly escape to the surface. As thermal energy rises through the mantle, it hits the lithosphere, fracturing the rigid crust into tectonic plates and forcing them into slow, constant motion. Over millions of years, this tectonic movement acts as a planetary thermostat. The shifting plates recycle carbon into the mantle, carve out the basins for our oceans, and push up the mountain ranges that direct global weather patterns. Without the superheated engine of the core, Earth loses its invisible shield and its thermal regulation. The surface becomes sterile, frozen, and airless. Above the crust, the atmosphere captures just enough solar energy to maintain an average surface temperature of 14.76 degrees Celsius. This temperature range is the reason the global ocean remains liquid across 70.8% of the planet's surface. It provides the stable environment necessary for complex organic molecules to assemble and interact. Maintaining this balance requires one final external stabilizing component, orbiting 384,400 kilometers away. This diagram shows how the Moon acts as a gravitational anchor. Its mass prevents the Earth's axis from wobbling chaotically, locking our tilt at exactly 23.4 degrees. This stable tilt ensures a predictable distribution of sunlight throughout the year. It provides the seasons we rely on and prevents the catastrophic climate swings seen on other planets. Life eventually became a part of this machine. During the Great Oxidation Event, early photosynthetic organisms began pumping oxygen into the sky. This oxygen formed the ozone layer, creating a chemical shield that blocked lethal UV radiation. The biosphere acts as a functional gear in the planetary engine, manufacturing the conditions required for life to leave the ocean and inhabit the land. These systems aligned to create the Holocene, an abnormally stable climate window that allowed human civilization to take root 11,700 years ago. Modern humans have since shifted from being reactive inhabitants of this environment to acting as a dominant geologic force. The expansion of industrial agriculture and fossil fuel extraction is now altering the atmospheric greenhouse gas composition faster than the planet's natural cycles can manage. This chart maps the 9 planetary boundaries, the physical limits of the Earth's engine. We have already crossed the safe threshold for both climate change and biosphere integrity, moving these systems into an unsustainable danger zone. Overloading the system results in measurable consequences: rising global temperatures, melting ice sheets, and an accelerated rate of species extinction. In the deepest scale of time, we know the final outcome. In roughly 5 billion years, the sun will expand into a red giant and vaporize the planet. The planetary machine is robust and will likely self-regulate for billions of years, with or without us. Our survival depends solely on maintaining the precise equilibrium that allows this machine to keep sustaining human life.